Eigenvalues and eigenvectors. This part is from section 5.1. And in this part, we are going to introduce the definition of eigenvalue, eigenvector, and eigenspace. Usually, eigenvalue and eigenvector comes into pairs, so we call this sometimes eigenpairs. So these two is referred by eigenpairs. So we basically have two questions. How do you find eigenpairs? This is the first question. Now, if you have eigenpairs, for each eigenpair, we are able to find eigenspace. So there are two questions, but the second question will be covered today, but the first question will be covered later. So let's first look at the definition of eigenpairs. So for n by m matrix A, if there are non-zero vector x and some scalar lambda such that they satisfy ax equals lambda x, then we call lambda as eigenvalue, which is a number, and x is called eigenvector. So lambda x together is eigenpairs. And very often we can have, for n by m matrix A, we can have n many eigenpairs, but not necessarily always like that. So we have to be, just keep in mind there might be potentially multiple eigenpairs exist for n by m matrix. Let's look at one example. So here we're not going to ask for a given matrix 2 by 2 matrix A, we're not going to ask how to find its eigenpairs, but we are going to give you a vector and try to verify if this is eigenvector or not. And if this is eigenvector, you want to find corresponding eigenvalue. And we also have some application of eigenpair. So this is application. So we are going to verify first question. So is U an eigenvector? To do that, we want to check is AU equals multiple of U for some lambda, for some number lambda. So this is what we want to check. So the left hand side is AU, which is 1652 and 6 negative 5. So we do regular multiplication. So this and this multiply together. 6 minus 30. And these two multiply. 30 minus 10. And compared to right hand side, which is lambda u, so that means lambda is multiplied to each component of u. So can we find some lambda potentially make this equal? The answer is yes. The lambda, when we take lambda as negative 4, this equality holds. So yes, U is an eigenvector, and with its value, eigenvalue, lambda equals -4. Now we look at application, a to the fifth to the u. So usually to find this computation, what we do is we do, by definition, a fifths means a. You want to multiply a 5 times and times u. This is very complicated computation. However, if you know that u is eigenvalue of a, then this computation can be simplified. So what we do is first we do it reversing. So we first do this au. We know that au is lambda u, where lambda is -4. So this is a, and the last one is lambda u. Lambda is -4, so we put lambda u. But lambda is constant, so we can always put this in front of everything. So this is basically lambda a to the fourth power u. And this is the same thing as lambda a to the third power au, and this is lambda u. So again, lambda squared a cubed u. If we keep going, at the end we have lambda to the fifth power u. And lambda to the fifth power u is simply -4 to the fifth power, which is numbers to the fifth power. And u is going to be 6 -5. So we can easily calculate so this is 1024 and 6, 5. Of course, for the end, the final answer, you need to multiply 1024 to 6 and -5. 6 and -5 separately. All right, now we're going to introduce eigenspace. Suppose lambda is an eigenvalue, then if and only if there exists a non-trivial solution a minus lambda ix equals 0. So why is that? We can look at the definition of lambda. So if lambda is eigenvalue, then there exists, if lambda and u is eigenpair, then we can write this au as lambda u. So we can write this as au equals lambda u. Or you can write au minus lambda iu equals 0, because I times u is always u. And then we can take out u as the common factor, so we can get a minus lambda iu equals 0. We know that eigenvector is non-zero vector, so that means a minus lambda ix equals 0 has non-trivial solution. All right, so this is first fact. Now let's introduce eigenspace. So eigenvectors corresponding to lambda forms a vector space. Now a minus lambda I. This is called eigenspace of lambda. So what it means is, now we know that for eigenvalue lambda, you need to solve this equation. This is a homogeneous equation. And if you solve this, then the solution set is, so the collection of solution is called null space of a minus lambda I. And this is basically collection of all eigenvalues associated to lambda, eigenvalue lambda, eigenvector, or associate, so right, it's not eigenvectors, so it's a collection of eigenvectors associated to lambda, eigenvalue lambda. And this is called eigenspace. So eigenspace is basically a collection of all eigenvectors associated to lambda. And the way to find it is to solve this equation, homogeneous equation. All right, so we can look at the next question, example. We have this A, the same, so we have this A, and verify that -4 is an eigenvalue. Actually, we did it in the previous question, so the same A, and we said we have -4 associated to one eigenvector. So in this previous example, we first give eigenvector and let you find corresponding eigenvector. Now this problem is opposite. Now we're going to give you -4 is eigenvalue and try to verify this is indeed eigenvalue of A. To do that, what you do is you want to solve a homogeneous equation A minus lambda I x equals 0. If there is non-trivial solution, so of course x equals 0 is solution, but this is a trivial solution. If there's non-trivial solution, then this is eigenvector. Then -4 is eigenvalue and x is an eigenvector. So we need to solve this. So if there exists non-trivial solution, then lambda equals -4 is eigenvalue. So the problem goes to how to solve A minus lambda I x equals 0. So A was 1652. A is 1652 and lambda is -4. So A minus lambda I x means 1652 minus lambda I, -4, -4, 0, 0, x. You want to solve this equals 0. So 1 -4, which is -3, and 6 minus 0 is 6, and 5 minus 0 is 5, and 2 minus -4, oh sorry, here's 1 minus -4 is 1 plus 4, and 2 minus -4 means 2 plus 4, and x, this is x, equals 0. Now we want to look at, to solve this, we can look at its augmented matrix, which can be reduced as R2 minus R1 goes to R2, which replace R2 as just 0, 0, 0. And the only pivot is the first one, and there is only one non-zero row. And that means this is basic variable, this is free variable. If you have free variable, then that means there's non-trivial solution. So because there is free variable, A minus lambda I x must have non-trivial solution, which means lambda equals -4 is eigenvalue. Now the second question. Now we know negative 4 is eigenvalue. We confirmed it. Now find the eigenspace of negative 4. This is basically the same thing as you want to solve a minus lambda ix equals 0. So in other words, we want to solve this augmented matrix and write it into PVF, parametric vector form. So this is 560. We need one more page. This is 560,000. And from here, we can, because this is 0 rows, it doesn't give any additional information. We can convert the first row as 5x1 plus 6x2 equals 0. And then solve for this basic variable, which means x1 equals negative 6 over 5 x2. And x2 is x2. For PVF form, you want to write its free variables just by himself. So x2 equals x2. Now that means x is negative 6 over 5, 1, and x2. All right. So this is eigenspace. Or you can write this as eigenspace as span of this vector, negative 6 over 5, 1. Now the last question is find the unit eigenvector of negative 4. So any solution of this a minus lambda ix is going to be eigenvector. So there are many eigenvectors. So if you take x2 equals 1, then this is eigenvector. If you can take x2 equals whatever you like, 100, then you can have another eigenvector. But different choice of x2 gives eigenvector with different length. Now you want to find eigenvector with a unit length, in other words, length 1. So remember that if you have some vector x1, x2, then what is length? Length can be written as this, and this is summation of squares and take the square root. So we want to look at here. First we look at this vector and multiply by something. We want to make it unit length. So the length, if you look at this x, the length of x is negative 6 over 5 squared plus 1 squared, and x2 is scalar, so you can just multiply x2 outside, so absolute value of x2. And I want to make this as 1s. By solving x2, you are going to find the unit length vector, eigenvector. So x2, and here this is 5 squared and 36 plus 25 equals 1. So x2 equals, so I can move this to the other side, 5, and here 50, 61. So that means if you choose x2 is either plus or minus of 5 over square root of 61, then this makes eigenvector as unit length. So for example, so the unit eigenvector is going to be unit eigenvector is x equals, in place of x2 I will write the number we find from above, and negative 5 over 6 and 1. So this, we actually find two unit vectors. unit eigenvectors in this problem. All right, we are going to stop here.